Okay, so now let's go to the last paper of this session, the K-link towards automating the generation of multi-step Infoleak exploits against the Linux kernel. The speaker is Lianzhen Chuan from UC Riverside.
It's very unfortunate that my work is about Linux kernel exploitation, but they put me in this machine learning session. So it's unfortunate, but I cannot change that. But maybe it's an opportunity of cross-session speaking. Let me introduce some background knowledge about memory error. As we know, operating system kernels are major targets of attackers. And the attackers usually corrupt memory errors to gain some advantage inside the kernel. What are memory errors? They're essentially read or write, program read or write in unintended ways. There are two famous kinds of memory errors. They are out of bound and use after free. Out of bound is the program read or write using an out of bound pointer. Use after free is the program read or write using a dangling pointer. And then here's some background of Infoleak. Nowadays, operating system kernels employ some defenses to prevent attackers from attacking the OS kernel. For example, KASLR is a modern defense that makes it difficult for attacker to construct end-to-end exploit. As you can see in the figure, and this is ASLR, not KASLR. I cannot find a figure for KASLR, but it's similar. It randomizes different kernel regions at boot time. Therefore, when at runtime, the attacker doesn't know the exact location of, for example, kernel code location or kernel heap location. To circumvent this defense, Infoleak is used by attackers. For example, when the attacker leaked a code pointer from kernel, he is able to locate the kernel code region. Infoleak serves as an important step in end-to-end exploits. There are two broad categories of Infoleak. One is side channel based. For example, attackers can utilize some microarchitecture side channel. The other category is memory error based Infoleak, where the attacker exploits memory errors in the kernel to leak sensitive information, like a code pointer, out of the kernel. In memory error-based Infoleak, the attacker needs to create an Infoleak data flow. As is illustrated in this figure, this data flow carries sensitive information to some leaking sink, like a function named copy to user. When sensitive information reaches the leaking sink, it will go to user space or network, where the attacker can retrieve the values. The goal of our work is to assist the automated generation of Infoleak exploits given a memory error. Of course, we also have a POC to trigger this memory error. Exploit generation has long been considered as an art. The attacker needs to craft his exploits carefully, but nowadays people has researched how to automatically generate exploit for a given bug or a vulnerability. It has completely changed how the defenders and attackers operate. So we believe our work is of importance. Here, let me demonstrate a motivating example. we assume an attacker is given a UAF read error, as you can see in this figure. We can see that in this figure, object AX25def is already freed, but its field values is read out and then written to object AX25. How can attacker exploit this vulnerability? And he needs to reallocate an object named mbus. This object is allocated on top of the freed object. Therefore, when the UAF read occurs, the field ubus is read out and finally copied to object x25 field n2. And this is because the field the offset of field ubus is the same as the offset of field values inside object x25def. And because the kernel has, because this object has similar size with the previous freed object, they can be allocated in the same slab in kernel. And now the sensitive information is stored in object x25. The attacker needs to invoke a new system call getSockOpt to copy the sensitive information out of the kernel through copy to user. Actually, there are multiple strategies to leak information. In the motivating example, we first utilize a UAF read and then followed by a new system call. There are other ways to do so. There are 3 technical challenges in memory error-based Infoleak. First, we need to model an intended data flow. We observed that memory errors are essentially invalid pointer dereferences that occur at a load or store instruction. You can see in this motivating example, it occurs at the UAF read operation. So we want to connect the data flow between this operation with another read or write operation. And here we want to connect the UAF read operation with the write operation in system call 0. Technical challenge 2, modeling data flow across system calls. In this motivating example, the attacker invokes a new system call 2 to read out the information. So we need to capture this in our work. Technical challenge 3, modeling additional memory errors. A single memory error may not directly be exploitable. But this doesn't mean we cannot exploit this error. We may take other path. We can create additional or intermediate memory errors and before finally discovering Infoleak. So here's our solution. To tackle the technical challenges, we propose a graph-based data flow reasoning and search framework. It can turn the problem of crafting Infoleak exploits into searching for data flow fragments in the graph. It has several unique features that can tackle the technical challenges accordingly. It handles everything through a unified graph search. And it can handle a large search space, which means it can cover multiple strategies to achieve Infoleaks, as is shown in this figure. So in our framework, the central data structure is MDFG, short for Memory Error Augmented Data Flow Graph. It consists of nodes and edges. Nodes include variable nodes, load nodes, store nodes. Edges include data edges and pointer edges. And different from existing implementation of DFG, our data structure is unique in that it has pointer edge, and it can model an intended data flow. So let me explain pointer edge, because exploiting memory corruption is mostly about corrupting pointers. So we have dedicated pointer variable nodes, and we have dedicated load nodes, store nodes. They are connected by pointer edge. Therefore, we can reason about the behaviors when a pointer is corrupted. And for unintended data flow, you can see in this figure the red edge. We add this data flow that shouldn't exist if memory error didn't occur. Here's the workflow of our framework. The input is Linux kernel code, as well as a memory error we are given. The output is Infoleak pass. There are three major steps in this workflow. One, extracting intended data flow. And the data flows is stored as a data structure MDFG. And this step is mostly static. Step two is extending MDFG with unintended data flows. Step three is to search the MDFG for Infoleak pass. And this step is both static and dynamic. So let me talk about the step in detail. So when extracting unintended data flow, we need to first perform a points to analysis for the kernel. After obtaining the points to information, we construct a graph. We construct the intended data flow graphs. This is done by creating nodes and link them with edges. And it is a summary-based interprocedural analysis. And then we extend MDFG with unintended data flows. And we need to model the memory error as capability. We model the memory error using the slab cache where it is located and the offset length of the error. With such capability, we can fit it into the workflow and then modify the MDFG. So let me explain based on this motivating example. We can see object AX25def is already freed. And then we find object mbus having similar size with AX25def. And we assume a successful heap function allows the object mbus to be allocated on top of object AX25def. Because of the two fields from two objects have the same offset. Therefore, the write and the read operation alias with each other. Therefore, we create this red edge to link them. So this is how we extend intended data flows with unintended data flows. So after extending MDFG with unintended data flows, we want to perform two kinds of searches on the graph. We search for Infoleak paths and control pointers. For Infoleak paths, we simply output them as our final results. For control pointers, they are essentially new additional memory errors. So they are fed into this framework again, or not again. They are free. They are newly found memory errors. So you can see it's an iterative algorithm. You can keep finding memory error. And then once you find a memory error, you want to extend the graph with unintended data flow introduced by this memory error. So in this way, you can cover the search space of different kinds of Infoleak strategies. When we search for Infoleak paths, we are looking for a path like this. The source is sensitive information, and the sink is some leaking sink like copy the user. When you search for a new memory error, you're searching for a path from attacker control value to some pointer. And this pointer will be used as the address of lower store. It's important that we want to use a dynamic verification to verify each data flow path. This is to avoid false positive, because not all Infoleak paths in our graph are valid. Sometimes the control flow graph is infeasible. Other times, the data flow paths are imprecise due to the imprecision of points to analysis. Therefore, we use a symbolic execution to verify each data flow. So here's our evaluation. We evaluate our framework using 250 syzbot exposed memory bugs. Syzbot is a continuous process from Google that has found many kernel bugs. In total, we find 4 kinds of Infoleak strategies. We can utilize a single read error to leak information. We found we can use a single write error to leak information. We can use a read error followed by a created read error to leak information. We can use a write error followed by a created read error to the information. In total, we are able to find Infoleak paths in 25 bug reports, in 21 bugs out of the 250 bugs. And we select 7 of them to craft end-to-end exploits. Here is some case study, and in this case, it can be exploited by a strategy called read error followed by a created read error. This is because the master object is freed object, and the attacker can control the master unique field, and then the master unique length field of this object. Therefore, in copy the user, he is able to create a new out-of-bound read error. So, here's another case study, and you can see that there are 3 out-of-bound write errors, which write several pointers out of bound. So the attacker needs to allocate an object to receive that out-of-bound write information. Therefore, he can copy the information to user space. We also evaluate our tools with 11 CVEs. And we are able to find Infoleak paths for 7 of them. However, we failed the remaining cases for the following reasons. First, our framework doesn't model the process of creating illegal free primitive. Second, we doesn't model Infoleak through control flow. We only model data flow Infoleak. Last, we cannot handle stack memory error. We focus on kernel heap memory error. Yeah, in conclusion, our framework can facilitate automation of exploit generation. The automation of Infoleak exploits for Linux kernel. We can uncover various exploit strategies. We find previously unknown Infoleak paths. Thank you.
All right, so any questions? So yeah, Professor Herbert, I think you definitely can give us some comments.
Hi, so really interesting work. Thank you for this. I have a clarification question because it wasn't entirely clear to me what the starting point is for your automation chain. So I know that you assume that you have a POC, right? So you have a vulnerability, you have an initial POC. Does that mean that you're not looking for an object, so in the UAF, the use after free vulnerability that you described, you're not looking for a particular object that can be placed in exactly that freed space on the slab, which has a code pointer which will then be leaked? Is that assumed? Do you assume that that's already there, or do you also include that part in your chain?
Okay, thank you for the question. First, our starting point is a POC. Because our evaluation set is from syzbot, so which is Google Continuous Processor that already provide us with the POC.
So the POC includes the the code pointer that will put in the right place in your object.
The POC gives us the information of where the memory error occurs. Mm-hmm. Like, for example, it occurs at kmalloc 256 slab. But it's our job to look for object of similar size.
Oh, okay.
So in our points to analysis, we already collected such information of object size.
Okay, so that answers my question. So you are looking for the right object sizes that have the right code pointer at the right offset.
Yeah.
Okay, thanks.
Yeah, nice talk. Thank you. And I'm interested in the details of pointer to analysis. Could you, because I don't see is there any details of pointer to analysis and what kind of you implement by yourself or use some existing framework of pointer to analysis?
I use an existing framework called Suture, S-U-T-U-R-E.
Oh, thank you.
So thank for the question, the speaker. So I guess that's all the papers in this session. So thanks for everyone for coming.